Okay, good morning again, everyone. So today my plan is to finish the shading slides, the shadow part and reflection part. And I will also quickly go over the entire set of slides to go over them to see whether there are some important parts that we have missed. You must have seen also just announcement in OptiClass about the intensity, using intensity to compute radiance at a point. It actually has some detailed area-based calculations, but in the homework we're not going to go into that much detail. The only detail that we will be using is the intensity of the point light source will already be provided in the homework file, and so you don't need to treat it the surface area of the point light source. It's just a point light source, so it will just be given as intensity, and the radiance, I mean the power of that intensity received at a surface patch, again, is not, we're not going to consider the area of the surface patch, because we're always going to try to compute what is the color of this point, a single point that we're intersecting at the surface of a sphere or a triangle. So there will be just a single points of intersection that we're going to be dealing with. Therefore, the only thing that you need to concern yourself is how that intensity reduces as the distance of that intersection point increases with respect to the light source. So we'll need to take into account the distance of the intersection point to the light source, and based on that we will have some quadratic attenuation, which means that quadratic decrease with respect to the distance, with respect to the distance. So the intensity that is going to be received at that point is going to decrease. And that's it's very simple to implement. Instead of using the intensity values directly in the assignment, you're just going to, since you already have the intersection point and the location of the light source, computing the distance is not a problem. So just multiply your intensity with a factor of 1 over d squared, and use that as the intensity at that point, intersection point. So at this point, we have seen how to, all these different parts of the basic elimination model. So this part that we have computed up to this point, it's called the basic elimination model. And it's composed of these 3 components. The ambient one, which is not dependent on any light source. It's the light available at every point in our scene. The diffuse, which is the light rays reflected in every direction from that point with respect to a light source, and then the specular component, which tries to model light rays that are reflected in a specific direction coming from the light source. So just like this is sometimes called mirror reflection. So this shiny patch, specular spot, it has different names. It is due to the specular component. Okay, so this is what we have covered up to now, and if we put all this together, so the color of an object at any point can be computed by adding. The model is additive, so the diffuse component, ambient component, specular component, all of them are edited, and this is a vector of RGB, red, green, blue components. So nothing different than what we have done up to now. So when we have multiple light sources in the scene, for each light source, diffuse and specular components will be computed for each light source, because each light source will not have a separate ambient component. The ambient is, as I said, it's not attached to any specific light source. The ambient is the light that is available, abundant everywhere in the scene. So we are going to compute the diffuse and specular components due to every one of those light sources and add them up. So everything is additive. If whatever the resulting value is greater than 255 that we want to put here, it's going to be clamped to the maximum value, meaning that that color has saturated at that point. So as you can see, 2 different light sources may result in 2 different surface shiny spots on a sphere. So this is a hint that there are 2 light sources here. Maybe there may be 3 light sources in this scene as well, at least 2. We can say, because there may be light sources which are illuminating the back of the spheres, which we may not see. So shinier objects have smaller shiny patches. So this one actually has a larger specular exponent. As these spheres go from left to right in this figure, the specular exponent increases. So this one you may it's like counterintuitive, but for example, isn't this more shiny? It looks more shiny. This bright spot is more bright. It occupies more places, but actually it doesn't also look realistic, because when an object is shinier, I mean, what happens is that mirror-like objects, since we only have a point light source, it's not an aerial light source, it's a point. So if it was a perfect mirror, the shiny spot that you're going to see here would be a single point if it was a perfect mirror, because there will be a single a light ray coming to this point. We will only be able to see it if our view angle is at a specific direction, if it was a mirror, and it will appear as a single spot. So this actually shinier objects, more shinier objects have larger specular exponents, and which makes this cosine alpha or cosine beta, whatever you call it, decrease faster to 0 as the angle moves away. But as you can see, when the angle is smaller, when you give specular exponent 1, which is the same as having the cosine alpha just reduces regularly, you may have a larger. And the reason that appears a lot of white here is due to saturation, basically. Okay, so you need to also very carefully to decide on those parameters to make the object look realistic. Which parameters should I give? What should be the specular exponent? What should be the color of the specular light? Okay, yeah, they are the same thing. But I say specular exponent, it's the CENG exponent. So this one here, P, sometimes written in some other books as S. They're exactly the same thing. So this Bilin-Fong shading, it's also called specular shading. So therefore, we need to have, I mean, this is the exponent. The larger it is, the faster this cosine alpha is going to converge to 0, the smaller that surface shiny patch is going to be. Its area is going to be smaller when this one is larger, which means that the object actually is more mirror-like. Okay. So we also need to, so this slide is actually one of the correction slides here, I think in specular. We need to, in order to make sure we compute the specular patch correctly, we need to also make sure this angle theta is not larger than 90 degrees. We need to first check. Specular reflection will only, just like diffuse, if we need to check whether this angle, the dot product, is positive. If the dot product is negative, we should actually just use 0 specular reflection at that point. So, sorry. We need to make this check whether the dot product of the normal vector and the half vector are larger, is a positive number. Okay, so I'm going to also overview everything, what kind of vectors we have in a configuration, what are the vectors we are going to compute, how we should also be careful about normalizing those vectors, which model uses which vector. For example, we will be using similar vectors when we are computing, for example, the shadows, or when we are computing the reflections from other objects. We will also be computing some vectors. So I'm going to overview all of them on GIMP on the whiteboard to summarize everything at the end of this lecture today. So yeah, that's putting it all together. We have these multiple light sources added up to get this color. So at this point, actually, the ray tracing algorithm is complete enough to get the a view of a scene that is like OpenGL like, no shadows, no reflections, but we have the primitive objects, we have triangles and spheres. If a scene is composed of entirely spheres and triangles, we should be able to generate pictures of this, photos of that scene that appear like this. Okay, so it's not bad at all actually. It looks good, but we can even make it with ray tracing. We can even make it better. So the algorithm so far is like this. For each pixel in our image, we compute this is the generate ray function. We generate the ray. We set the intersection point to some maximum number and the object intersect an object to null. So this is where for each object in our scene, we intersect our generated ray with the objects, and if it intersects at a point X, we maintain this point X. If it's an intersection that is closer than this T minimum, we keep track of which object was intersecting closest and the closest intersection point as well. If object is not null, so when can object be null? It may be null if our ray intersects none of the objects in the scene. In that case, we are looking at some background. What we can do is we can just there is sometimes called environment mapping, in which we can imagine a box surrounding our virtual scene, and we can map some pictures of faraway places to this box to do some environment mapping, like clouds, skybox. We can put a skybox so that it doesn't appear dark. Okay, if you want some natural looking background, we can just map these pictures behind and set the color to that one, whatever the color. So our ray actually is going to hit that skybox. If your entire camera is inside a large box, it's going to intersect with some triangle eventually, okay? If it's inside a box. So sometimes this is what, I mean, actually, most of the time, this is what people do when they're visualizing their virtual worlds. They put the entire scene in a skybox. In that case, the background color is given, for example, sometimes as a 2D RGB array, which is called a texture. Okay, so you're right. We're going to see learn something called texture mapping, which will be able to map those 2D RGB arrays also onto the surface of regular objects. Okay, not only rectangles like skyboxes, but we will have a triangle, for example, a triangular object with some arbitrary shape and with triangular meshes, and we'll be able to map that 2D RGB array as if its color is changing on its surface points from point to point. So just like that, a 2D RGB array, as you indicated, can be given to the faces of the skybox, which we will use to assign to our color. Yes, it can be done like that. But if our ray intersects with an object, we just set the color to the pixel color. If we do this, for example, this is, I think, the object color. This is actually this is the one that uses the basic elimination model. So this LO, the color of the object, which is this here. So LOXWO, the color of the object at point X, with this viewing vector. So VO is the unit vector from S to E. Our viewing direction, basically, our ray direction, basically. So we set the pixel color computed with respect to these parameters, and our ray tracing algorithm produces these images so far. Now, how are we going to make it better? By introducing shadows. Actually, shadows is the easiest part of ray tracing, and with just a simple, like 5-6 lines of additional code, your scene is going to get much better. It will include shadows with just one additional check. When you're computing that diffuse color or specular color for a light source, we already have, look at this vector WI. And this is the intersection point. So this WO is the to view or to eye vector. So let me turn on annotate. So this is, we compute this vector, which we call the to-view vector in the program, in the code that we have written. So this is our I. So this W is a unit vector. We compute the health vector. We have the normal of a point of that surface. All these vectors are what we have up to now. And this Wi is the to-light vector. Okay, so we also have this to-light vector. Now, if I so yeah, let me change this to a pencil. Okay, let's assume I create this ray, which let's call this ST. Look at this ray equation. It starts at x plus WI t. Okay, look at this ray equation that starts from here, goes to the light. Now, all I need to do is, if this ray equation, again, I do the same thing. Okay, if you write your ray tracing in a modular way, you'll see that we're actually executing the same thing over and over again in different parts. For example, what I need to do now is, for example, to find this point x, I intersected this ray, which was RT is equal to E plus dt. So this was my ray, okay? And I intersected it with all the objects to find this intersection point x. Now, I do the same thing. Look at this ray. All I need to do is execute the same function to figure out whether this ray that originates from x and goes in the direction of to light ray, if it intersects an object between x and between the light's position. Okay? Now, how can we do that? For example, if you know the distance between x and Wi, actually you're going to be computing that, right? For example, let's call the distance between L and x and L. For example, let's give it, for example, let's call it G. Okay. Now, if there's an intersection, if this is my ray and Wi is unit, if it's a unit vector, okay. But if it's a unit vector, if there's an intersection in which t is between 0 and G, what does this mean? If there's an intersection with an object in which this ray intersects with an object, and the intersection occurs at some t between 0 and G, where this G is the distance from x to L. What it means is that you get exactly the situation where is similar to the one in the picture. There is an object in between the point and the light source, point light source. What does this mean? It means that this point x is in shadow. Okay, if there's such an intersection, you will. And another different thing from the. But at this point, if you find such an object which satisfies this t between 0 and G, you can actually break out of your for loop of looking at all the other objects. For example, if you find this red sphere that is in between light source and x, do you need to go ahead and find to see whether there are other objects that are closer to us? No, right? I mean, the existence of one object between x and light, and imagine, I mean, just also know that in this simple ray tracing, we don't have any transparent objects. If we have a transparent object, we need to take this into account in the shadow as well. But just assume all the objects are opaque. And in that case, the existence of any one of these objects between x and L guarantees a shadow. Therefore, in your for loop, in the shadow intersection, you need to tell your function that finds ray object intersection that this is actually an intersection test for shadows, so that you break out of the for loop early, just for optimization, basically. What happens if you don't break out of the for loop early when you find such an object? You continue doing the intersection for the other objects. Will it produce wrong results? No, it will still work, but it will be unnecessary. If you find an object, there is no need to look for other objects. By the way, if there is no shadow, you'll still need to go do intersection tests with all the objects. Okay, the bad thing about these shadow rays, just like those background rays, is that you still need to check your ray against all the objects, even if the intersection is not successful, to see whether there's such an object. But as soon as you find an object with intersection between 0 and g, where g is the distance between x and l, you're just going to terminate your for loop, saying that, okay, we have found ourselves, so this is a shadow case. When there's shadow, what are you going to do with 4 shadows? Nothing, basically. Just ignore this light source when you're adding the diffuse and specular components, meaning that this light is not going to contribute to the diffuse and specular component that we add for this point x. One small point here is, look at this. I want to just turn your attention to this part where we are checking this inequality, 0 less than t. Since these are floating point numbers, what happens is that the object, the surface itself, look at this rectangle that x belongs to. It's actually one of our objects, right? The rectangle that x belongs to is one of our objects. So it's possible that if you don't check a special flag that's saying, or example, just in these intersection tests, avoid intersection with x's original object, x's own object. So if you don't avoid it, if you just blindly intersect with all the objects in the scene, at one point your ray is going to intersect with this object that x belongs to, in which case there will be an intersection at t is equal to 0, right? In a perfect world, t is going to be exactly 0, but because of floating point imprecision, we will sometimes have t a very small positive number, like 0,001, for example, okay? And it will intersect at this point. So this inequality may actually be satisfied for the object itself. So this will produce some kind of these floating point precision errors will produce some noise, shadow noise around at this x, okay? Sometimes it's going to be, for some points it will be no shadow, for some points it will be shadow. So actually this object, this sphere, is going to produce a noisy shadow here. So what in reality we do is, we determine some epsilon, depending on our floating point or double precision. Instead of checking this t against a 0 directly, we check it against this epsilon. Okay, so whether if t is larger than epsilon, then we treat that there is a shadow for this light source. Okay, and another thing that you can avoid you can do to avoid this shadow noise is actually to avoid intersection of your ray completely with the object itself. Okay, so if you, for example, when you're sending your ray to your function, you also send this additional parameter saying that this is the triangle, or you can just send a reference to your triangle, some ID of your triangle. This is the triangle that X is actually on. So in your intersection test, when you encounter this triangle, just don't do intersection, shadow intersection for that triangle. If you do that, you can actually check against 0. Okay, so this is, and this, as you can see, to write this code, there's, in terms of computational novelty, you're not doing anything new. You have a ray, you have objects, you do ray object intersection tests. The only thing that changes is how you make those, if you just write an if statement checking whether it's between 0 and g. By the way, if this wi is not normalized, imagine I have this light vector, let's call this light vector, and if I have this light vector specified as L minus X, okay, if this light vector is L minus X, non-normalized, it means that the intersection that you're checking is going to be between 0 and 1. So if t is between 0 and 1, so then there will be shadow. So depending on how you maintain these vectors, you should always be careful about the lengths of your vectors. if the to light vector is the non-normalized version that you use for as shadow rays, that G unit you're going to be using is going to be 1. Because when t is 0, you're here. When t is equal to 1, you'll be here. If this to light vector is how you write your shadow ray. So to light times t. So if this is your shadow ray, it will be between 0 and 1. Okay, any questions about shadows? And shadows are really actually important in terms of how they provide us some visual cues as to how we interpret a scene. So it makes your scene really nice. But in order to have shadow, you need to have, for example, your spheres should be on some tabletop, some triangles. So actually, objects cast shadows on other objects. So you can have actually 3 or 4 shadows. You can arrange them in such a way that, and you can arrange your light source location in such a way that one sphere is going to cast shadow on the other one. And but yeah, if you have multiple light sources, your shadows actually can be interesting. Some half shadow, and the shadow boundaries actually are going to be very sharp. We don't have soft shadows here because if you're checking for a pixel, there will be binary decision for each point on the surface. There's a binary decision. Is it in shadow or not? Okay, we don't look at this neighborhood, but we are going to see in OpenGL, we are going to implement shadows ourselves. In that case, we'll see techniques to actually interpolate its neighborhood. For example, we can look at this 5 by 5 neighborhood, looking at the 5 pixels around it. Actually, these are continuous points, but just imagine this X actually belongs to a pixel in our image. So if we generate other 25 rays, which will actually be intersecting with some neighbor points of this X, and ask the question, how many of these 25 neighbor points are in shadow, how many are not? And using this to produce an average kind of some continuous shadow, this is a way to continue soft shadows. So why do we have soft shadows in real life? Because light sources are not point light sources in real life. The reason we have sharp shadows in the images that we will generate is that there's a point light source. A point light source is just a point, its shadow is going to be very strict. It's a binary decision, okay? But in real life we don't have point lights. We have aerial lights which span a certain area, and therefore shadows are, the boundaries of the shadows are smooth. Okay, yeah, so this is the same thing here. The shadow right, and if there's an intersection, we just say it's a shadow. And yeah, this is the discussion on epsilon. The same thing, so to avoid self-intersection. And there are different ways to avoid self-intersection. This is also indicated here on this slide. Now, the ray tracing algorithm so far is, now we have here for each light source, we compute a shadow ray to that light source, and we intersect our shadow ray with each object. If the intersection occurs before the light source, it seems there is a shadow. When we continue the light loop, we just proceed to the next light. If it's not in shadow, only if it's not in shadow, we compute the diffuse and specular components and add it to our pixel color. And as you look at this, look at these shadows on this figure. It immediately makes the scene much more realistic. The shadows are really good, and as you can see, some shadows are darker. The shadow point between these two spheres is darker than this shadow because of multiple light sources. I think there are 3 point light sources in this scene. I can see 3 patches, this one, and this one. Therefore, there will be 3 different shades of shadows. For example, this point on this table is probably in shadow with respect to one of the light sources, but it's not in shadow with respect to the other light sources. So we add less amount of light sources to this point on the table. Now, the final part of the ray tracing is what makes ray tracing algorithm difficult actually. Up to this point, there is nothing recursive about it, so you can get these images easily by adding some only minimal stuff to what I have provided on Oculus as the program that we have written in class. You can extend it so that the images that you produce appear like this easily. There is no recursive ray tracing, nothing at all. So this last part, which we just actually we are going to discuss, it's only in Tensilize actually. In terms of coding, this is the most difficult part. But it's not super difficult. You should be able to do that, this part as well. But the first time I was implementing ray tracing like 5-6 years ago. By the way, the first time I implemented ray tracing myself was when I was teaching in this course, and it was super fun. And I think it was the first time as a programmer experience. It was the first time I had to use some mutual recursive functions, a recursion which two functions calling each other kind of, but you don't need to have a mutual recursion. It was due to the way I designed my code. I had to have this mutual recursive function in my ray tracing code, but if you design it better, I'm sure you don't need, you'll just be able to do it with just simple recursion. Okay, so where does this recursive part come? Why is it recursive by nature? Okay, so this up to this point, actually, we get really good pictures. Do we really need recursive ray tracing? And why do we need it? The reason we need is that if we have objects that are reflective, for example, that in which we not only see the light sources, the specular patches here, but there are also light rays bouncing off other objects that hit this object and is coming towards us. For example, it maybe if this was like a mirror-like reflective object, the blue ball, we should see some blueness on this green sphere if it's like a mirror-like object, just like the image I showed you here. I think it was so I maintain what was it, 477? Yeah, I think it was in 2019. Not this one, or earlier than that. No. So this is a public some repository that I maintain. I think in 2004. I think it was the first time I implemented. Yeah, here. Horse and mug high resolution. So yeah, I've shown you this picture, and as you can see, look at this red sphere, and look at the tabletop. The tabletop itself is a gray. It's composed of two gray triangles. Although it is gray, we see some green point on the table itself. Why do we see this gray table as green at this point? We see it as green due to the reflecting light rays coming off this green ball, green sphere. So if you look at the ray tracing algorithm so far, we don't have these reflections from other objects. We have shadows, we have interactions of light sources with the object surface itself, but at this point, all we got is object's color, or some shadow, some ambient color. Even if in shadow, it's still multiplied with the object's color itself. The objects, a point on a surface of an object will never get the color of other objects on it. Okay, up to this point, we don't have the reflection. So this last part is to add these reflections from other objects. And for that, we're unlike this, it's similar to specular component, but in specular component we had this specular patch to actually we allowed it to be wider than a point. In this reflective part, however, if we did the same thing in reflections, we would actually see these green reflections as kind of blurred. Okay, for example, the boundary of this red, the boundary of this green reflection you see here is really sharp, right? But in specular reflections, those specular spots, it had some area, which if it was sharp like this, we would see the specular reflection as a point only. Okay, so therefore the light rays coming off this object, we are going to assume that they're only going to be seen along a specific ray direction. This is how reflections are going to be computed. But it's not as green as the ball itself. That's what happens in reflections. The reflective ray, we are going to multiply, we are going to attenuate it, we are going to make the effect, the light rays coming from other objects' reflections, we are going to reduce them by multiplying it with some reflectivity constant for that, which will be dependent on the material of that object. Okay, for example, if an object is this reflectivity constant is 1.0, it means that the reflective ray contributes to the those color component directly with no attenuation, with no decrease in reflectivity. If it's 0.5, it's like whatever the color we compute for the reflection ray, it's going to be, the color is going to be dimmed, it's going to be reduced by 50% and then added to the surface color. So that's the reason these green, for example, parts are not as greenish as this one, because we are adding gray other parts and it gets reduced. And one thing that is interesting here is another, so sometimes the reflection we see, for the reflection may continue. If this green ball was reflective by itself, points on its surface will not be whole green, but for example, we could maybe see the reflection of this cup on the ball as well, and then we would see this reflection back on the table. So it's actually, it continues, it's like a reflective process, is iterative. Everybody may reflect on each other. So it's this is how that recursion step is going. A very good question, Selim. So these reflective rays, do we attenuate the intensity as the distance of the reflective objects? For example, if the distance of this green spot between this X spot that do we attenuate it with the distance between these 2 points? I think we should attenuate to be more realistic, but in the assignment, you're not going to do that as far as I know. It should be specified clearly. If it's not, you can ask this question on COV 2 to clarify it with the assistant, how he implemented that. But this is just, again, a choice of design. I think attenuation with respect to the distance make this reflection ray more realistic, because this is what will happen in real life, right? I mean, if you have a very far away object, the light rays bouncing off that, if you're going to reflect those, you should take into account distance. It should decrease with distance, but to simplify things or to increase speed, sometimes we make these abstractions and we may ignore certain things, and this may be one of those things. It may be the distance between the reflection point and this point may be ignored. We can ignore the distance and use, since it's already attenuated by reflectivity, we may not consider the distance as well. So it depends. My answer is it really depends on how you want to do it, but to be more realistic, it should decrease with distance. Yeah, maybe it's they may have forgot to give this detail, but let's see. But if it's not specified in the assignment like this, our reference should be the book or how we describe this on the slides, and let's see how the slides do that. Okay, so this is where we do the recursive ray tracing, where what we are going to do is this. So this picture shows it nicely. So this is our primary ray. So, and this is the reflection ray. So what is this reflection ray? It is computed actually by with the reflection, so this is the normal of the surface. So this is the surface normal at that point. So this reflection ray is just like if there was light source coming here, only the perfectly reflected light is going to come towards our primary ray. So this, it's like the angle of incidence of our primary ray with the surface will be equal to the angle of reflection here. Okay, so we didn't compute this reflection in the health vector specular case, but for recursive ray tracing, we have to compute these reflective rays correctly. Okay, so we compute this reflection ray. Now the question is whether then this reflection ray, if you look at this reflection ray, and this point was x, look at this new ray. RT is equal to x plus this reflection ray. Oops, it just went, so I just deleted that or deannotate when, yeah. So it just disappeared. So, but so let me quickly write it. So consider this ray. RT is equal to x plus this reflect, let's call it reflect t. Okay, so which is this reflection direction. Look at this vector. So this this ray equation is nothing but another ray, as if this was our pixel that we want to compute. So if the question that I will do recursively now is, what is the color of this reflective ray? Which object it intersects first? So it's exactly whether, and this may be in shadow, we don't know. So, but at this point, this reflection ray is like we are looking at, we are trying to construct another image at this, as if this X is our pixel. What color would that be? So at this point, we run recursively the exact same algorithm for this new ray, compute the color, and multiply this color with some like 0.5 or 0.3, whatever the reflectivity constant for this surface point is, we attenuate it with respect to that and add it to our color we compute. Now, the question here is that, do we also take into account the length of this reflection vector when we are doing this attenuation? So let's see. And another thing is this recursive computation does not continue infinitely, because it may be the case that the reflected rays may stuck. The reflection may continue and continue intersecting with objects infinitely back and forth. We are going to have another parameter in our ray tracing input scenes that says what is the number of ray tracing steps that you need, the recursive steps, before you actually end that recursion. So it's called the depth of the recursion ray tracing. And in practice, people use 2, 3. So the recursion doesn't go too deep, actually. We only need to go 2, 3 recursive steps. Now, here is and here is how that reflective ray is computed. So the reflection is computed with respect to this formula. Given the view vector, given the normal, and cosine theta is nothing but the angle between the view vector and the normal along the surface. So look at this formula on the right hand side. It contains only our view vector to view vector, which is unit, and the normal vector on the surface. So if you apply this formula, you would find this reflection ray. And this light is computed. As you can see, there is no attenuation with respect to the distance. So there is no attenuation with respect to the length of WR. For example, if what you're saying is that if to make it more realistic, we could have divided this L by, for example, the length of whatever. Actually, this WR is a unit vector, but we may use the actually, yeah, what we need to do is, whatever that t is, the closest t that we will find later, if you divide it by t square, if you divide this part by t square, you would have your attenuation that you suggested. But this shows that we are not doing that attenuation. The attenuation, we don't consider that with reflection colors. Okay, so we directly multiply it with this mirror reflection coefficient, which tells us how mirror-like this surface is. For certain objects, if this mirror reflection coefficient is 0, you don't need to do any recursive ray tracing at all. Okay, because for objects, for example, if your intersection point on the object happens to be a matte object like this cube, then or this green sphere here, as you can see, it's not reflective at all. For those, you don't need to continue recursive ray tracing. You can just make that reflect. You can just stop your ray tracing at this point. So there's no attenuation with the reflection rays. So you should implement this by this default way, which is simpler, less time consuming in terms of computation, but you may try the other way to see whether how realistic your reflections are going to look like. But right now we just apply this simple formula, and this is how you should do in the assignment. And putting it all together, we have this basic illumination model, we have this mirror reflection component, which is computed recursively by following these lights, and at the end we get ourselves, if this table is recursive, in addition to the shadows, as you can see, we have this faded, if the table, for example, has this mirror reflection coefficient, for example 0.3 or 0.2, it will have some contribution from these green and blue spheres as well. So right now, with the addition of shadows and this mirror reflection, our images look like this. I also think that just like we had this in specular, I mean, another thing we don't do, for example, we don't attenuate with respect to distance. This loses realism. Another thing actually in these reflections that will look better is that just like that billing foam component where we had this shiny patch having an area around that spot, that shiny, that will hit our eye. We could actually blur the edges of these reflecting. I mean, in real life, these reflections actually, depending if it's not completely mirror-like, the reflections are not as sharp as the objects themselves. Okay, so you may also think about how you can make this tabletop appear realistic by blurring the reflection, but that will make it probably computationally very difficult. It's not just a single point light source for you have to, so you can actually, by increasing the computational complexity, it could be done. It will make your reflections look more realistic. But again, in this introductory course, we just use this simplest, the most simple model of where our reflections are just look as sharp as the objects themselves, only a little bit dimmer. Their intensity is reduced, the reflections intensity is reduced because we multiply this with this L. The mirror reflection is computed by multiplying the recursively computed intensity with this Km. That's what makes it dimmer, reduced intensity. But other than that, they are as sharp as the objects themselves. Okay, so the ray tracing has a lot of other things that can employ to make it look more realistic, more efficient to compute. There are data structures that we use to speed up intersection tests. This is very important. Adding textures to ray tracing. We are going to see some of those in the upcoming weeks, but you're not going to implement these in the first homework. These are not mandatory in the first homework. Acceleration structure, I think there's the first homework has a bonus part, so I should have the first homework. I think, I don't know whether it's the first part or the last part. I mean the first version. I think this is the most up-to-date version. Yeah, you're only going to have attenuation for the surface points themselves. Now, point light, vertex data, hints and tips. Yeah, there's a bonus part, this 5. So 5 points, I mean, if you're interested in this 5-point bonus, actually it may require a lot of work for just 5 points. I don't recommend you to do that if you're busy, you have other things. But if you're really interested in ray tracing and finish your assignment earlier than the deadline, if you still have time and you want to work on it, the most important thing that will speed up your ray tracer will be an acceleration structure, which is like indexing your triangles, objects in the scene in a hierarchical tree by subdividing your space into regions hierarchically, and then you're doing the intersection test first only with the large parts. Like, for example, if you just simply, for example, if you just divide your entire scene into 4 equal regions like this, and imagine you have a ray that is here. I mean, your ray doesn't intersect with this 2 left regions completely. So you first test the intersection of the entire region. If your ray doesn't intersect with the entire region, just a single test, you skipped all the thousands of triangles in this region in one shot. Threading may also, parallelizing it may speed it up too, but since we don't have GPUs, maybe, I mean, in 4 threads or 8 threads, you can speed up 4 times or 8 times, but an acceleration structure is going to provide a speed up, a logarithmic speed up. Okay, so the speed up you're going to get from an acceleration structure will be incredible. I mean, just a 1 hour rendering time is going to be reduced to like 2 seconds. So therefore, the key here is using an acceleration structure. But yeah, threading using multiple threads for different parts of your image is also worth trying. But as I said, it can just provide you a linear speed up in terms of the number of threads that you use. The other is really logarithmic speed up. I mean, reduction will be the log of your number of objects in your scene, so it's tremendous. There are others like modeling non-point light source, adding textures, transparent objects, refraction, fog, smoke. So it's really doing ray tracing. So this one actually is about threading, for example. How can you use the thousands of GPU cores to speed up ray tracing? It's still a linear speed up, but 1000 factor. So when it may be linear, but you have 1000. If this linear factor is 1000, it may be worthwhile to consider it. So this is what ray tracing on the GPU is about. It's about threading and how you can use the large number of cores GPU provide you to speed up ray tracing in a parallel manner. And Ozoja gives an advanced ray tracing course. It's a graduate course, but I think undergrads can take it as well. So if you're interested in ray tracing and want to learn more about it in the subsequent semesters, you may consider taking that course. And these are some ray trace and texture map images, which look at these reflections. And the reflections also are not. I think this image also uses this technique that I mentioned, non-sharp reflections. It blurs the reflections on the objects, which it makes it look more realistic. This is another way to look at these. The transparent objects, even the refraction. When the light is refracting, the wavelength of the light. I mean, you get these rainbow patches on this. I mean, it looks amazing. And even the shadows. In the shadows, we have these refracted different. The white light is different wavelengths of the white light is reflected and passed through in different angles, so that the white intensity light source is divided into different color light sources here, and we have these amazing images. So we are not going to see how to do those, but just these are like teasers for the advanced ray tracing course. Probably they do it in that course like this. Okay, so that's it. We have finished everything about what is necessary for you to do your ray tracing assignment. Okay, and you're all out of time, actually 5 minutes over time. That's it for me for today. If you have any questions while you're doing the assignment, please let us know. Don't hesitate to send emails to assistants, to us, also Jana, okay? And have a nice weekend. We are going to start with the new topic on Tuesday next week. Okay, I will stop sharing now, and I will stop recording.